Right now, somewhere on Earth, someone is staring at the sky, watching the impossible. The sun vanishes in the middle of the day. Or the moon bleeds red at midnight. You've seen the photos. You've heard the stories. But here's what most people get wrong: these two events are not opposites. They're not even close. One happens because the moon blocks something. The other happens because the moon receives something. And that single difference changes everything about what you see, where you see it, and why ancient civilizations built entire religions around moments that last less than 8 minutes. By the end of this journey, you'll understand exactly why a solar eclipse can only touch a tiny ribbon of Earth, while a lunar eclipse paints half the planet red. You'll know why one demands eye protection and the other invites you to stare. And you'll discover the precise cosmic geometry that makes both events so rare, yet so predictable that NASA can tell you the exact second of an eclipse 300 years from now. Let's start with the basics. Because everything hinges on one simple fact most people forget: the moon orbits Earth. Earth orbits the sun. These three objects are locked in an endless gravitational dance, and twice a month, they almost line up perfectly. Almost. The moon crosses between Earth and sun at every new moon. It swings behind Earth at every full moon. So why don't we see eclipses twice a month? The answer lives in a 5-degree tilt. The moon's orbit isn't flat. It's tilted roughly 5 degrees relative to Earth's path around the sun. Most months, the moon passes just above or just below that perfect alignment. It misses. But 2 to 5 times per year, the geometry clicks. When the moon slides directly between you and the sun, its shadow races across Earth's surface at over 1,000 miles per hour. That's a solar eclipse. You're standing in the moon's shadow. The sun disappears, and for a few precious minutes, the universe reveals secrets normally hidden by blinding light. When Earth slides directly between the sun and moon, our planet casts a shadow into space. The moon drifts through it. That's a lunar eclipse. The moon doesn't vanish, it transforms. Sunlight bends through Earth's atmosphere, filters out blue wavelengths, and paints the lunar surface in shades of copper, rust, and blood. Dr. Fred Espenak, NASA's legendary eclipse calculator known simply as Mr. Eclipse, spent decades mapping these celestial alignments. His calculations reveal something profound: every eclipse belongs to a family. A cycle called the Saros. 18 years, 11 days, and 8 hours. That's how long it takes for the sun, moon, and Earth to return to nearly identical positions. The same eclipse geometry repeats, shifted slightly westward around the globe. This means eclipses aren't random. They're clockwork. Ancient Babylonian astronomers discovered this pattern 3,000 years ago, without telescopes, without computers, without any understanding of orbital mechanics. They simply watched. And counted. Over the next 4 parts, we'll dive deep into both eclipse types. You'll walk the narrow path of totality where day becomes night. You'll watch the moon turn crimson from the comfort of your backyard. You'll meet the scientists who chase shadows across continents, and the instruments that capture light from the sun's hidden corona. But first, you need to understand the shadow itself, because the difference between a total eclipse and a partial one, the difference between witnessing cosmic majesty and merely noticing the sky dim slightly, comes down to where you stand within a cone of darkness racing through space at 1700 miles per hour, and that shadow has two parts with very different names. The moon casts two shadows. Not one. Two. The first is called the Umbra. A cone of complete darkness where sunlight is entirely blocked. If you stand within the Umbra during a solar eclipse, the sun vanishes. Stars emerge at noon. The temperature drops. Animals fall silent. This is totality, and it only touches Earth in a narrow band rarely wider than 170 miles. The second shadow is the Penumbra. A larger, softer zone of partial darkness spreading thousands of miles in every direction. Stand here, and you'll see the moon take a bite from the sun. Impressive, but not transformative. The sky dims. Shadows sharpen. Most people don't even notice unless someone tells them to look up. Here's what changes everything about the difference between solar and lunar eclipses. During a solar eclipse, you must stand inside the shadow. The moon is small. Its umbra barely grazes Earth's surface. Miss that narrow ribbon by 50 miles, and you miss totality entirely. During a lunar eclipse, the geometry flips. Earth's shadow is enormous, over 2.5 times the moon's diameter at lunar distance. The entire moon fits inside our planet's umbra with room to spare. Anyone on the night side of Earth sees the same event. No chasing required. No special location. Just look up. Ancient observers understood this asymmetry long before they understood why. The Babylonians recorded eclipses on clay tablets over 4,000 years ago. They noticed lunar eclipses appeared frequently, visible across entire empires. But solar eclipses? Rare. Local. A city might witness totality while villages 30 miles away saw nothing unusual. This inconsistency terrified them. How could the gods darken the sun for some, but not others? Greek astronomers began solving the puzzle around 500 BCE. Anaxagoras proposed that eclipses were shadows, not divine interventions. Aristotle noticed Earth's shadow on the moon was always curved, evidence our planet was spherical. But the full mechanical understanding took centuries more. Then came Hipparchus, working on the island of Rhodes around 150 BCE. Hipparchus made the first accurate measurement of the moon's distance from Earth. His method was elegant. He compared observations of the same solar eclipse from two different locations, and used the parallax difference to triangulate distance. The moon, he calculated, was roughly 30 Earth diameters away. He was remarkably close. The actual number is about 30.1. Dr. John Steele, a historian of ancient astronomy at Brown University, describes Hipparchus as the first scientist to treat eclipses as precision instruments rather than omens. His work transformed celestial events from messages into measurements. But here's the complication no ancient astronomer could explain: eclipse paths don't repeat in the same place. The Saros cycle brings similar geometry every 18 years, but shifted. A total solar eclipse visible in Egypt won't return to Egypt for centuries. Some locations wait over 300 years between totalities. Why? The answer involves three competing cycles that almost, but never quite, synchronize: the moon's orbit around Earth, Earth's orbit around the sun, and a third motion almost no one discusses: the slow rotation of the moon's orbital plane itself. That 5-degree tilt from part 1. It's not fixed. It wobbles, completing one full rotation every 18.6 years. This wobble means the nodes, the 2 points where the Moon's tilted orbit crosses Earth's orbital plane, drift slowly backward through the zodiac. Eclipses can only occur near these nodes. And the nodes never stay still. Ancient astronomers saw the patterns. They recorded them. They predicted them. But the wobble remained invisible, a hidden variable corrupting their calculations century after century, until someone finally caught it. The wobble was hiding in plain sight for 2,000 years. Islamic astronomers working in Baghdad during the 9th century finally pinned it down. They called the drifting nodes the dragon's head and tail, mythological names for mathematical precision. By tracking eclipses across generations of meticulous records, scholars at the House of Wisdom calculated the nodal precession period with stunning accuracy. 18.6 years. The same number modern astronomers use today. But knowing the wobble existed didn't answer a deeper question: why should anyone care about eclipses beyond predicting them? For millennia, eclipses were spectacles, omens, calendar markers. Useful, but ultimately just shadow play. The sun vanished, then returned. The moon reddened, then recovered. What more was there to learn? Then astronomers pointed telescopes at the sun's edge during totality, and discovered an entire realm of fire invisible at any other moment. The corona, a halo of superheated plasma extending millions of miles into space, but so faint that the sun's blinding surface drowns it out completely. Only during total solar eclipses, when the moon blocks that overwhelming glare, does the corona reveal itself. Wispy, structured, impossibly hot, over 1 million degrees, compared to the surface temperature of roughly 5,800 degrees. This made no sense. How could the sun's outer atmosphere be 200 times hotter than its surface? Heat should dissipate with distance, not intensify. The corona broke thermodynamics. Or so it seemed. Dr. Madhulika Gathakrita, NASA's heliophysics lead, calls the coronal heating problem one of the most stubborn mysteries in solar physics. Decades of eclipse observations, space telescopes, and theoretical models have narrowed the possibilities, but the complete answer remains elusive. Every eclipse brings new data, new constraints, new chances to solve what the sun refuses to explain. Lunar eclipses offered their own revelation. When Earth's shadow swallows the moon, something unexpected happens. The moon doesn't go black. It glows. Deep red. Sometimes copper. Occasionally gray if volcanic ash or pollution fills our atmosphere. That color is a message, a fingerprint of every sunrise and sunset happening simultaneously around Earth's limb. Sunlight passing through our atmosphere bends inward. Blue wavelengths scatter away. Red wavelengths curve into the shadow cone and reach the moon. Scientists now use lunar eclipse spectra to study Earth's atmosphere from the outside, as if our planet were an exoplanet transiting a distant star. But the true turn came on May 29, 1919. British astronomer Arthur Eddington led 2 expeditions to photograph a total solar eclipse, one to the island of Principe off West Africa, another to Sobral, Brazil. His target wasn't the corona. It was the stars near the sun's edge. Albert Einstein's general theory of relativity predicted that massive objects bend spacetime, and light passing near the Sun should curve slightly, shifting the apparent positions of background stars. Newton's gravity said light shouldn't bend at all. The eclipse would decide. Clouds plagued Principe. Equipment failed in Sobral's heat. But enough photographs survived, the stars had shifted. Exactly as Einstein predicted. Eddington's announcement shattered 3 centuries of Newtonian certainty. Gravity wasn't a force pulling through space. Spacetime itself curved around mass. The New York Times headline read, "Lights all askew in the heavens." Everything we thought we knew about the universe, rewritten by a shadow. Dr. Peter Coles, cosmologist and science historian, describes that eclipse as the moment modern physics was born in public. Not in a laboratory. Not in equations alone. In the moon's shadow racing across the Atlantic. Eclipses were no longer just celestial clockwork, they had become laboratories. Testing grounds for the deepest laws of physics. Windows into stellar atmospheres and planetary climates. Tools for understanding not just our solar system, but every star system in the galaxy, and we were only beginning to ask the right questions. We've been thinking too small. Solar eclipses taught us the Sun has a secret atmosphere burning at impossible temperatures. Lunar eclipses taught us Earth's air leaves fingerprints on borrowed light. The 1919 expedition proved gravity bends spacetime itself. But the real revelation came when astronomers stopped looking at our moon, and started looking for shadows around other stars. In 2009, NASA launched Kepler, a space telescope with one mission. Stare at 150,000 stars simultaneously. Wait for something to cross in front of them. Wait for an eclipse. Not our kind of eclipse. Transits. Distant planets passing between their stars and our telescopes. The same geometry that creates our solar eclipses, scaled across light years. The results shattered expectations. Within 4 years, Kepler confirmed over 900 planets. Within a decade, thousands more. Rocky worlds. Gas giants. Planets orbiting 2 suns. Planets so close to their stars that years last hours. Dr. Natalie Batalha, Kepler mission scientist, described the flood of discoveries as the moment humanity learned that planets aren't rare. They're everywhere. And here's the synthesis that connects everything. When the moon blocks the sun, we call it a solar eclipse. When an exoplanet blocks a star, we call it a transit. When Earth's shadow engulfs the moon, we study refracted light through our atmosphere. When an exoplanet's atmosphere passes in front of its star, we study the same refraction, searching for oxygen, methane, water vapor. Signs of life. The technique we use to analyze blood moons is the same technique we use to hunt for habitable worlds. James Webb Space Telescope now does this routinely. In 2022, Webb detected carbon dioxide in the atmosphere of WASP 39b, a gas giant 700 light-years away. The method: transit spectroscopy. Watching starlight filter through alien air during an eclipse we'll never see with human eyes. Dr. Nicole Colon, Webb's exoplanet observation scientist, explains the connection simply. Every transit is a natural experiment. The universe blocks its own light for us, and we read what's written in the shadow. But our own eclipses still hold secrets. The coronal heating problem remains unsolved. We know magnetic field lines erupt and reconnect in the Sun's outer atmosphere. We know these reconnection events release tremendous energy. But the precise mechanism transferring heat outward, still debated. Every total solar eclipse brings researchers to the path of totality armed with spectrometers, polarimeters, and high-speed cameras. Each dataset constrains the possibilities further. NASA's Parker Solar Probe, launched in 2018, now flies through the corona itself, the first human-made object to touch the Sun. But even Parker can't replicate what eclipses provide. A view from outside. A clean silhouette. The corona's full structure visible against the black lunar disk. And lunar eclipses now serve as calibration tools for exoplanet research. By studying how Earth's atmosphere filters sunlight during a blood moon, scientists test the same models they apply to alien worlds. If we can detect ozone in our own shadow, we can detect ozone around a star 40 light-years away. The geometry hasn't changed since Hipparchus calculated the moon's distance. Sun, moon, Earth. Star, planet, telescope. The same alignment. The same shadows. The same science, scaled from miles to light years. Open questions remain. Why does the corona's temperature spike so dramatically? What can transit spectroscopy miss? Are there biosignatures we haven't imagined yet? But the real question isn't what we've found. It's what it means to live on a planet perfectly positioned to witness both kinds of eclipses, and use them to decode the universe itself. You live on the only known world where total solar eclipses look the way they do. This isn't poetry. It's geometry. The Sun is roughly 400 times larger than the Moon. But it's also roughly 400 times farther away. These two ratios nearly cancel, creating an almost perfect visual match in our sky. The Moon appears just large enough to block the Sun's blinding surface, and just small enough to reveal the corona's ghostly fire. No other planet in our solar system experiences this. Mars has two tiny moons that cross the Sun like specks of dust. Jupiter's moons are too small relative to the Sun's angular size. Saturn, Uranus, Neptune, none produce the precise silhouette we see from Earth. Dr. Frank Close, Oxford physicist and author, calls this coincidence a gift with an expiration date. The Moon drifts away from Earth at roughly 1.5 inches per year. In 600 million years, it will appear too small to fully cover the Sun. Total solar eclipses will end. Future life on this planet, if any survives, will never see the corona with naked eyes. We exist in a window. A brief cosmic moment when shadows align perfectly, and we've learned to use that window. Upcoming eclipses are already scheduled into NASA mission timelines. The total solar eclipse crossing North America on April 8, 2024 drew over 30 million people into the path of totality. Scientists deployed high-altitude balloons, synchronized ground observations across 14 states, and captured coronal data impossible to gather any other way. Future missions will go further. The European Space Agency's Proba 3, launching soon, will create artificial eclipses in space, two spacecraft flying in precise formation, one blocking the Sun for the other. Permanent totality. Unlimited observation time. The corona studied not for minutes, but for hours. Yet something irreplaceable remains in the real thing, standing beneath a vanishing sun, watching the moon's shadow race toward you at 1700 miles per hour, feeling the temperature plunge as twilight erupts in every direction. No simulation captures this. No spacecraft replaces the visceral awe of totality. Lunar eclipses offer a different gift: accessibility. Visibility across half the Earth. A slow transformation you can watch with family, with friends, with strangers who happen to look up at the same moment. The moon turns red not through violence, but through the collected light of every sunrise and sunset on Earth, bent gently into shadow. Remember the question from the beginning: what's the difference between a solar eclipse and a lunar eclipse? Now you know. Solar eclipses are rare, local, and demand you travel to the shadow. Lunar eclipses are generous, global, and invite you simply to witness. One reveals the sun's hidden atmosphere. The other reveals Earth's atmospheric fingerprint painted on the moon. But both share the same truth: they exist because three objects, Sun, Moon, Earth, occasionally align with mathematical precision across millions of miles of empty space. And for reasons we still don't fully understand, we're here to see it. Carl Sagan wrote that astronomy is a humbling and character-building experience. Eclipses prove him right. They remind us that we orbit an ordinary star in an ordinary galaxy, yet we've decoded the shadows well enough to predict them centuries ahead and use them to search for life around distant suns. The next eclipse is already coming. The geometry is already in motion. Somewhere on Earth, someone will stand in a shadow, and look up. Will it be you? Close your eyes for a moment. Imagine standing in an open field. The air is still. The sky is wrong. Not dark exactly, but dimmed, as if someone slowly turned down a cosmic dial. Around you, the horizon glows in every direction. Sunset colors. Sunrise colors. All at once. 360 degrees of twilight. Then the shadow arrives. You don't see it coming. You feel it. A wave of cold washing over your skin. The last sliver of sun vanishes behind the moon's ancient edge. And suddenly, stars. In the middle of the day. The corona blazes outward like frozen lightning. Birds fall silent. Dogs whimper. Somewhere nearby, a stranger starts to cry. This is totality. This is what our ancestors believed was the death of the sun. This is what Babylonian priests feared and Greek philosophers decoded, and modern scientists still travel thousands of miles to witness, even though they already know exactly what's happening, because knowing isn't the same as feeling. We've journeyed through the mechanics. The 5-degree tilt. The Umbra and Penumbra. The 18-year Saros cycle that ancient astronomers discovered without telescopes or satellites. We've met Hipparchus measuring the moon's distance with nothing but geometry and patience. We've watched Eddington prove Einstein right beneath a vanishing sunday. We've seen NASA's Kepler telescope find thousands of worlds using the same shadow geometry that creates our eclipses, but here's what all those facts add up to: you exist at an impossible intersection. A planet where the moon appears exactly the right size to block exactly the right star at exactly the right distance to reveal secrets hidden any other time. A civilization that evolved intelligence, built mathematics, invented telescopes, launched spacecraft, and used shadows to rewrite physics. A moment in cosmic history, brief, fleeting, already ending, when total solar eclipses are still possible. 600 million years from now, they won't be. The moon drifts away. 1.5 inches per year. Invisible in a human lifetime. Unstoppable across geologic time. Future creatures on this planet, if any exist, will never see the corona with naked eyes. They'll know it exists. They'll have our records, our photographs, our data. But they'll never stand in that field. Never feel that cold. Never watch stars emerge at noon. We are the witnesses. The ones who happened to be here when the geometry still worked. And what about lunar eclipses? The ones that ask nothing of you but to look up. There's something democratic about a blood moon. No plane tickets. No path of totality. No racing across continents to catch a 3-minute window. Just half the planet, invited to watch the same slow transformation together. The moon doesn't vanish. It deepens. Copper. Rust. Sometimes the color of dried roses. That light traveled 93 million miles from the sun, bent through Earth's atmosphere, filtered through every sunrise and sunset happening simultaneously around our planet's edge, and landed gently on a world 240,000 miles away. You're not watching darkness. You're watching Earth's shadow, painted in the colors of home. Think about what that means. Every lunar eclipse is a message from our own atmosphere. Every solar eclipse is a window into stellar fire. Every transit of a distant planet is an echo of the same geometry, scaled across light years, used to search for oxygen, methane, water. Signs that we're not alone. The shadows taught us the sun has a hidden corona burning at impossible temperatures. The shadows taught us gravity bends light. The shadows taught us planets orbit other stars by the billions. The same simple alignment. Moon crossing sun, Earth crossing moon, planet crossing star, unlocked secrets we couldn't have imagined when the first humans looked up and trembled. And we're still learning. The coronal heating problem remains unsolved. Exoplanet atmospheres are just beginning to reveal their chemistry. Somewhere right now, a graduate student is analyzing eclipse data that might answer a question no one has thought to ask yet. The universe keeps teaching. The shadows keep falling. The only question is whether we keep watching. So here's what stays with me. Eclipses are not about the sun. They're not about the moon. They're about alignment. About rare moments when separate things, orbits, distances, angles, timing, converge into something greater than their parts. Isn't that what we're all searching for? Moments when chaos resolves into clarity. When scattered efforts suddenly connect. When you stand in exactly the right place at exactly the right time, and the universe shows you something you couldn't have seen any other way. Those moments don't come often. They don't wait. And they don't repeat in the same place twice. When was the last time you stopped everything and looked up, not at your phone? Not at a screen. At the actual sky. The one that's been there since before humans existed. The one that will still be there long after we're gone. Have you ever witnessed an eclipse? Solar or lunar? And if you have, what did you feel in that moment? Wonder. Insignificance. Connection to something ancient and ongoing. If you haven't, what's stopping you? The next lunar eclipse is visible from wherever you are. No travel required. No special equipment. Just your eyes. Just your time. Just your willingness to pause, and here's the deeper question: what else are you missing, simply because you forgot to look? The geometry is already in motion. The moon is drifting through space right now, curving toward its next appointment with the sun's edge or Earth's shadow. The dates are fixed. The paths are calculated. April 8, 2025. March 14, 2026. August 12, 2026. The eclipses will happen whether you're watching or not. But they won't mean anything unless someone witnesses them, unless someone stands in the shadow and feels the ancient chill. Unless someone looks up at the blood moon and remembers that the red light traveled through their own planet's air. Unless someone connects the geometry in the sky to the geometry inside, the rare alignments that make a life feel whole. If this resonated with you, if these kinds of conversations matter to you, if you want to stay in the loop when the next cosmic alignment approaches, consider staying connected, not because I'm asking, but because the universe keeps sending invitations. And it would be a shame to miss the next one simply because no one reminded you to look up. The shadow is coming. Will you be there to meet it?